In earlier lecture we have seen that how one can convert the integral equation of Gauss law in electrostatics, Gauss law in magnetism, Faraday law and Ampere's law. The combined form of these four equations is known as Maxwell equation in electrodynamics. Now in this particular section of the video we will see that the inconsistency into the Ampere's law. So what is that inconsistency and how one can derive the result for that? This is the purpose of this lecture. So for this particular point I am using the differential form of the Maxwell equation, that is basically Ampere's law. So in general we define the Ampere's law in differential form del cross B is equal to mu naught times J, where B is the magnetic field density and J is the current density. So one can also derive from integral form to the differential form by using the Stokes theorem. If suppose I have to derive the result of Ampere's law from integral form to the differential form, so the integral form of the Ampere's law is closed path integral B dot dl is equal to mu naught times the current, which is enclosed by the current loop. So in the first section I am just deriving the result of this Ampere's law in terms of the differential form. So we know the Stokes theorem that provide basically a relationship between the closed path integral of any field. Here I have considered that B. So closed path integral of this magnetic field is equal to the open surface integral of curl of this field del cross B dot ds. So this is the statement, mathematical statement from the Stokes theorem, where in the left hand side the closed path integral of the magnetic field, and into right hand side this is the surface integral of the curl of that magnetic field, which field basically I have considered here, that is magnetic field. So this is equation number 1, which is the Ampere's law in differential form. So the result will be, if I put the value of equation number 2 into number 1, it becomes left hand side. This is open surface integral del cross B dot ds is equal to mu naught times I, that current which is enclosed. But now I have to modify the right hand side by using the current density term in. So the current can be defined as I is equal to open surface integral J dot ds. So instead of this I can write this open surface integral J dot ds. So the term becomes mu naught open surface integral J dot ds. And in the left hand side this is the curl del cross B is scalar product, and you can say this is the surface integral of the curl of the magnetic field. So now one can compare both the sides. So after comparison we get this result del cross B minus mu naught times G dot ds is equal to 0. So after comparing these two sides, we found this particular result. So now we have to check that which term is equal to 0, either of these two. So this one or that ds. ds is the area and that could not be 0. So this term del cross B minus mu naught times J will be equal to 0. So del cross B minus mu naught J is 0. And if this is equal to 0, so one can find out the result del cross B is equal to mu naught times J. This is the Ampere's law in differential form, which I have written here. So del cross B is equal to mu naught J. Where is the problem with this Ampere's law? Where is the inconsistency? So we have to check basically that particular point and have to introduce one more term, that is called displacement current. So I am using this Ampere's law in differential form. So first of all, I have to take the divergence of this equation. The divergence of this equation will be del dot del cross B is equal to mu naught times del dot G. So by taking the divergence of this particular equation, we found that left hand side is equal to 0, because the divergence of any curve is 0. So this mu naught del dot G will be equal to 0. Mu naught is a constant and cannot be 0, so del dot J is equal to 0. So from this operation we found that del dot J is equal to 0. Now if I conclude this result, then I found that this is true only when we use direct current. This result is valid only for the direct current. It means the Ampere's law is valid only for the direct current. The logic in favor of this statement is the continuity equation. In continuity equation, we see that del dot J is equal to d rho upon dt. This is our continuity equation, which I explain about the charge conservation. The charge cannot be created, not be destroyed. So del dot J is equal to d rho upon dt. If in this continuity equation, the current is, nature of the current is direct, then d rho upon dt for direct current will be equal to 0. d rho upon dt is equal to 0 for DC current, for the direct current. So one can find here that del dot J is equal to 0. So from the continuity equation, when we apply the nature of the current, we found that del dot J is equal to 0. And the same idea when we apply here into the Ampere's law by taking the divergence, we found del dot J is equal to 0. It means this law satisfies the condition, and one can conclude that this Ampere law in the present form is valid only for the direct current. So what will be the additional term? If suppose we apply the alternating current here, then what will be the nature, what will be the form of the Ampere's law? This is the point, this is the topic. So for that, Maxwell modified the Ampere's law by using the displacement current. So modification of Ampere's circuital law with the help of displacement current. So what is the nature of displacement current? How one can define it? These are some basic points. So for this purpose, we have considered here the Ampere's law in differential form. Del cross B is equal to mu naught times J plus JD, where JD is the displacement current density. An additional term we have introduced into the Ampere's law that represent to the displacement current. So now we are taking the divergence of this equation. This JD is the displacement current density. So the first step is divergence, taking the divergence of both sides. We found this del dot del cross B is equal to mu naught del dot J plus del dot JD. So here at the first step, what I did, I just take the divergence of the first equation, and as a result I observe this result. And we know that divergence of the curl is equal to 0. Divergence of the curl is 0. So left hand side is 0, and we observe only that this factor, right hand side mu naught, and this multiplication factor is equal to 0. So again there will be 2 points, either mu naught is equal to 0 or the second factor is equal to 0. Mu naught cannot be 0, so del dot J we can write, after putting this value here, that mu naught could not be 0, so del dot J plus del dot JD is equal to 0, and hence the result can be written as like this: del dot J is equal to minus del dot JD, or just rearranging the term. So I am writing del dot JD in left hand side is equal to minus del dot G. So now is the second step, and at this particular step I am putting the value of continuity equation into right hand side. So by using the continuity equation, which is del dot J plus d rho upon dt is equal to 0. So del dot J is equal to minus d rho upon dt. Del dot J is equal to minus d rho upon dt. So I am putting this value of del dot J in this particular equation. So this equation becomes this minus, and this minus becomes plus, and del dot J is equal to d rho upon dt. So this is d rho upon dt. So this statement came from the continuity equation, and I have right now this del dot JD is equal to d rho upon dt. Suppose this is equation number 3. So now in the third step, I have to use Maxwell equation. Del dot E is equal to rho upon epsilon naught. So from here one can compute the result that rho is equal to del dot epsilon naught E, and epsilon naught E is the electric field intensity. It is represented by the D letter, vector D. Vector E is the electric field density and vector D is the electric field intensity. So it can be written as del dot D, but I am using as it is del dot epsilon naught vector E. So now I have to put the value of this rho in the equation number 3. So it becomes del dot JD is equal to d upon dt, and the value of rho, that is del dot epsilon naught E. So this is del dot JD, and now further rearranging the terms, it can be written as del operator dot epsilon naught dE upon dt. So del dot JD is equal to del dot epsilon naught dE upon dt. This is equation number 4. If I compare both sides, I found that GD is equal to epsilon naught dE upon dt, and this is time varying electric field. So JD in terms of the time varying electric field. So the modified Ampere's law in terms of the displacement current can be written as in this form: this del cross B is equal to mu naught times J plus mu naught times JD. JD is this one, mu naught epsilon naught dE upon dt. So now the modified Ampere's law can be written in this form. In general, we use this Ampere's law to find the magnetic field at any point because of the current by using the closed loop. So here this is the displacement current density contribution into the Ampere's law. So what is the nature and what is the form of displacement current? This is the point right now after deriving the result for the displacement current. So we see here this is mu naught epsilon naught dE upon dt, and dE upon dt, as I mentioned earlier, represent to the time varying electric field. This dE upon dt is time varying electric field. So now if I apply the idea here in this particular circuit in which a capacitor is attached with the source. So in the first case I have considered here a battery. So I current flow from this side to that, and we know that capacitor block the current. So current is available here, and suppose further I have to find out the magnetic field at this particular point P1 because of this current. So I have to use Ampere's law. So because of that I have to draw a closed loop in which the current is enclosed. So here the current is enclosed through this closed path or closed loop. So one can apply the Ampere's law here, because in integral form you have seen that d dot dl is equal to mu naught times I. And if I suppose the radius of this closed loop is r, so the magnetic field will be constant at every point. R is the radius or height from the square of this particular point P1, where we are trying to find out the magnetic field. So B is constant at every point of this closed loop, so it comes out from this closed path integral, and dl is equal to B into 2 pi r. The value of this integration will be 2 pi r if r is the radius. So B into 2 pi r is equal to mu naught times I, and hence the value of B is equal to mu naught upon 2 pi I upon r. This is the magnetic field at any point by using the Ampere's law. So B is equal to mu naught upon 2 pi into I upon r. So one can find, or one can use the Ampere's law to find the magnetic field at any point. So in this situation there is no problem to apply the Ampere's law. But if suppose in this particular case at the center of this capacitor, that is P2 point, and height is of it is R, again that is same. So according to the Ampere's law, there is no current is bound with this closed loop. If somehow I draw the closed loop through this distance, then we cannot apply the Ampere's law, and as a result there will be current 0. So B will be equal to 0 at this particular point, right? So there is no possibility of the magnetic field at this situation. The form of the loop may vary. So if suppose I use this particular shape, this is open and this is closed, so still there is no current bound, so the magnetic field at this particular point P2 will be 0. So now if I introduce the displacement current, then in this particular situation what will happen? In the first case I have used direct current, and we know that capacitor basically block the current, and there will be no current in between the capacitor. So as a result there will be no magnetic field for this situation. But if I use alternating current here, then the capacitor work, and as a result in a one cycle the plate charge will be positive, and on the other cycle, half cycle, it will be negative because of this region. This is positive, this one is negative. So in a half cycle the first plate will be positive, and in that time this will be negative. So basically a electric field developed inside the capacitor, and this is the direction for that particular time. As the cycle change, the direction of the field also change. In addition to the variation into the magnitude of the electric field, of the current. So as current will change, the magnitude of the current change, the magnitude of the electric field will also change. So when we apply the alternating current for this case, we found that there is time varying magnetic field inside the capacitor plates. So there is a point, there is a concept basically similar looks like into the Faraday law. In Faraday law we know that time varying magnetic field produce the electric field, and similarly here at this particular case the time varying electric field will produce the magnetic field, and this is the situation. So here in between these two plates of the capacitor, the electric field basically varies, and as a result of that a magnetic field will produce. So that magnetic field one can calculate by using this Ampere's law. So in this particular case this term basically plays the role. Here we observe time varying electric field. So in the displacement current, the time varying electric field basically produce the magnetic field. So this is the modified Ampere's law. So now del cross B is equal to mu naught times J plus mu naught epsilon naught dE upon dt. This is the mathematical form of the displacement current, and one can see the displacement current in between the plates of capacitor in terms of the time varying electric field, and the idea is again same. So by this way one has removed the inconsistency into the Ampere's law. So this was the modified law. Thanks.